Hi, everybody. Thanks for being here today for our second CosmoVerse Training Series session with Dr. William Giarè. Thank you, William, for accepting our invitation today. CosmoVerse, as you may know, is a network of over 400 researchers in Europe and 600 globally, with the aim of unifying efforts in confronting the question of cosmological tensions and understanding how different parts of physics can contribute to that effort. Dr. William Giarè is currently a postdoctoral researcher at the School of Mathematics and Statistics at the University of Sheffield. He obtained his PhD from Sapienza University of Rome under the supervision of Alessandro Mercuri in 2021, and under whom he also studied during his MSc and undergraduate degrees. He has been a postdoctoral research fellow at the Galilei Institute for Theoretical Physics in Florence. William has also been awarded several research networking grants. He has been a mentoring supervisor on over 5 PhDs. In this training session, he will present the latest approaches to inflationary cosmology, taking us from theory to data analysis. William, please start in your own time.
Thank you very much for the nice introduction, and thank you very much for the invitation. I'm very glad to give these online training lectures. And the lectures are going to be on the very same topic, namely, this is going to be an introduction to inflationary cosmology, where I will try to cover different topics ranging from theory to data analysis. And I will try to give you a broad introduction to the standard model of cosmology. I will try to explain why we want to introduce inflation in the cosmological model and what kind of problems inflation can solve. Then I will try to explain what is the easiest way to introduce inflation in the cosmological model. So we will review single field literal models of inflation, and we will characterize their predictions at the background level. And then we will study inflationary perturbation theory. We will try to understand what are the predictions of inflation in terms of the primordial spectra, both for scalar and tensor perturbations that I will opportunely define. And then we will do some calculations where we will try to derive the expressions for the primordial spectra predicted by inflation. Once we derive the theoretical prediction of inflation, we will try to connect these theoretical predictions with what we actually observe in the cosmic microwave background radiation. So there will be a part where I will try to connect the theoretical predictions of inflation to what we actually measure in the cosmic microwave background. Once I've done that, I will try to give you a very broad and introduction and overview of the current observational constraints on the inflationary universe and its properties. The first part of the lecture, where I will cover this theoretical stuff, will take probably 1 hour and 20 minutes or something. After that, we will just, if I have enough time, I will just give you some introduction to some very important codes and numerical codes that we can use in cosmology to compute this theoretical prediction in a numerical way. So I will try to start with an introduction to GAMB, and I will show you some notebooks where I will explain you the basic stuff of these numerical codes. And if I have enough time, I also will give you an overview of some codes that you can use to do MCMC analysis and to analyze the output of these methodologies. So I will now start with this theoretical part that should take more or less 1 hour and 20 minutes or something. So I will start with a very broad overview of the standard model of cosmology. Right now, our best understanding of the universe is summarized by the so-called lambda cold dark matter or lambda CDM cosmology. This model relies on 2 pillars of well-understood physics. On the one hand, we have GR, general relativity, to describe gravitational interactions. On the other hand, we have the standard model of particle physics to describe all the other interactions we observe in nature. However, as I will try to argue in these lectures, cosmology right now is a data-driven field. We can measure stuff in the universe, and we can try to understand the properties of our universe through observations. And along the years, it came out that GR and the standard model on their own are not enough to explain everything we observe. And the standard model of cosmology relies on at least 3 other ingredients that are inflation, cold dark matter, and dark energy, that are not so well understood within our model of fundamental interactions, but that are absolutely needed to explain observations. Inflation by itself is a phase of fast accelerated expansion of the universe that we believe occurred at very early times, when the universe was about 10 to the power of minus 35 seconds old. And as we shall see, we need inflation to set the initial conditions for the model to work. Then we need cold dark matter, which is a form of non-baryonic matter that should represent the vast majority of matter in the universe, and that we need to explain several observations, including the cosmic microwave background radiation and the large-scale structure of the universe. Finally, we need dark energy, a phase of energy with negative pressure that we need to explain observations that are telling us that the universe currently is accelerating. So you see that in the cosmological model, we need two accelerated phases of expansions. In this lecture, I will focus on inflation, that is the very base of the cosmological model and of the Landau-CDM cosmology. So I will start trying to explain why we need inflation. Originally, inflation was introduced in the cosmological model to solve some problems related to the initial conditions. And in particular, here I will go somehow very quickly, because I guess you are already more or less familiar with the problems that inflation can solve. But nevertheless, I will try to review the two most important problems that inflation can solve. One of them is the so-called horizon problem. So what is the problem? The problem, again, is that we can measure stuff in the universe. One of the most important things that we can measure is the cosmic microwave background radiation. This is an electromagnetic radiation made of photons. These photons decoupled in the very early universe, when the universe was 380,000 years old. And since then, they can freely travel until we can measure them today. And today, we can measure these photons and their temperature. And we find out that all these photons, coming from very different directions in the sky, share the very same physical temperature within some very tiny fluctuations of order of 1 part in 10 to the power of 5, that we will study in the second part of this lecture. But if, at first approximation, all these CMB photons share the very same physical temperature. And without inflation, this represents a problem for cosmology, because essentially we can look at how our universe looked like in the past. We can essentially look within our past lifetime until we reach the so-called last scattering surface. The last scattering surface corresponds to the cosmic time when these photons decoupled in the early universe. And we can try to understand the causal structure of the last scattering surface in terms of conformal diagrams, namely diagrams where light is here represented here by these lines. And in particular, if we focus on two different regions on the last scattering surface that we can call A and B, we realize that these regions on the last scattering surface were never in causal contact, simply because between the last scattering surface and the hot Big Bang singularity, you do not have enough conformal time for these past light cones to intersect. This means that the last scattering surface should consist of 1,000 causally disconnected regions. The question becomes, how it is possible that photons reaching us from these 1,000 causally disconnected regions could share the same physical temperature? Without inflation, you would need to assume very fine-tuned initial conditions in all these regions on the last scattering surface. And this poses a very important problems with initial condition, a very important fine-tuning problem. Inflation can brilliantly solve this problem, because what inflation actually does in terms of conformal diagram is to push back in conformal time the hot Big Bang singularity, so that now there is enough conformal time for these past light cones to intersect. So if you introduce inflation in the cosmological model, you can simply explain the high level of homogeneity that we observe in the cosmic microwave background simply in terms of causal contact. These photons were in causal contact in the early universe. And this is one of the reasons why inflation was originally introduced. Another problem that inflation can brilliantly solve is related to the spatial geometry of the universe. Again, we can measure stuff in the universe, we can measure the cosmic microwave background, we can measure the large-scale structure of the universe, we can measure distances in the universe. Once we collect all this information together, well, we discover that currently, at the present time, the universe is flat, or at the very least, nearly flat. And flatness poses a problem without inflation, because in mathematical terms, I would say it's not a tracking solution of the Friedman-Robertson-Walker dynamics, meaning that if we define the curvature density parameter omega k, this is going to be a function of time. And in a radiation-dominated universe, omega k will grow proportionally to the scale factor to the power of 2, while during a matter-dominated universe, omega k will grow as the scale factor. Therefore, if we measure omega k equal to 0 today, and we do, this implies that omega k should be extremely close to 0 at early times. And for instance, in the Planck epoch, when the universe was extremely old, very close to the Big Bang singularity, well, omega k should be as small as 10 to the power of minus 64 if we want to remain in agreement with current observations. So the question now becomes whether it's reasonable or not to assume fine-tune initial conditions within a precision of 1 part of 10 to the power of minus 64. And again, inflation can solve this problem, because what inflation does is to introduce a phase of accelerated expansion where omega k scales proportionally to 1 over the scale factor to the power of 2. And the scale factor is exponentially growing during inflation, meaning that the space-time is exponentially stretched towards flatness. And so one prediction of inflation, if you want, is that currently the universe should be spatially flat. And this is another important problem that inflation can brilliantly solve. So these are two reasons that essentially motivated us to introduce inflation in the cosmological model. The question now becomes, how can we introduce inflation in the cosmological model? I will review the easiest way that we can adopt to introduce inflation in the cosmological model. And in particular, I will argue that we can obtain inflation from a single scalar field minimally coupled to gravity. Namely, we can write down this very simple action. In red, you have the Einstein-Hilbert action from which you can get Giarè. And in green, you have the action of a scalar field phi with a potential V of phi. I will argue that you can get inflation from this very minimal theoretical setup. The only thing you need to do, the only price you need to pay, is to put some very weak restrictions on the inflationary potential, on this potential V of phi. So starting from this action here, the very first thing you can possibly do is to minimize the action with respect to the scalar field. You take the derivative of the action with respect to the scalar field, and you impose that they are equal to 0. If you do so, you can derive the equation of motion of the scalar field, which is known as Klein-Gordon equation. Now, I don't have time to do any explicit calculations in these lectures, but nevertheless, I provide in these slides some step-by-step derivations for the most important results I will be discussing. And you can find more notes, more information in the notes that are in the shared Google Drive folder. There are some written notes there where many calculations are also performed. Anyway, if you minimize the action with respect to the scalar field, you get the equation of motion of the scalar field, the Klein-Gordon equation. This equation dictates how the scalar field evolves over time. Another thing that you can do is to minimize the action with respect to the metric tensor. If you take the derivative of the action with respect to G mu, the metric tensor, and you impose that this is equal to 0, you get the expression for the stress energy tensor of the scalar field. And in particular, you can define the energy density associated with the scalar field and the pressure associated with the scalar field. Again, the step-by-step derivation of this equation here, you can find it in the right side hand of the slide. Once you have the energy density and pressure of the scalar field, if you assume that during inflation, the energy density of the universe and the pressure of the universe is dominated by the energy density of the scalar field and the pressure of the scalar field, this essentially becomes the energy density and the pressure of the inflationary universe. And you can write down the Friedman equation to try to understand what is going on. And in particular, the first Friedman equation will tell you how the Hubble parameters evolves during inflation. And this is given by the energy density, while the second Friedman equation will tell you what is the behavior of the scale factor, and in particular will tell you about AW dot, the second order time derivatives of the scale factor. By definition, during inflation, you want a phase of accelerated expansion. This means that AW dot should be positive. So from the second Friedman equation, you immediately see that if you want a phase of accelerated expansion, you need to require that the pressure of the scalar field should be smaller than minus the energy density divided by 3. So essentially, if you want a phase of accelerated expansion, you need to require that the effective equation of state W, which is defined as the pressure divided by the energy density, should be smaller than minus 1/3. In fact, you see that if you use the expression we derived for the energy density and the pressure, this relation is trivially satisfied if the energy density of the scalar field, if B of phi is dominant compared to the kinetic energy. If B of phi is dominant in this ratio, W is getting to the asymptotic value of -1. This value is called the Sitter limit, because when W is equal to -1, the spacetime is approaching a spacetime, a de Sitter spacetime, a de Sitter geometry. And not only you get an accelerated expansion, but the scale factor will exponentially grow and the Hubble parameter will be exactly constant in the de Sitter limit. So you can push this forward and you can derive other relations that are known as low roll conditions. And these low roll conditions set some restrictions, as you see, or some relations that the inflationary potential and the Hubble parameter should satisfy. And these low roll conditions are derived in detail in the notes that are on Google Drive. Now you see that essentially these are relations linking the inflationary potential, the derivatives of the scalar field, and the Hubble parameter. You can define some slow roll parameters, epsilon and eta, that will play an important role later on in the discussion, and that are always defined in terms of the inflationary potential and its derivatives with respect to the scalar field. During inflation, both these parameters must be much smaller than 1. Therefore, if you want to get inflation from this action here, the only thing you need to require is that these low roll parameters, these low roll conditions hold true. And again, you see that this is just meaning setting some restrictions on the inflationary potential and its derivatives in order for this equation to be satisfied. However, these are very weak conditions in a sense, because they do not fix the shape of the inflationary potential. You have plenty of freedom to choose whatever potential you like. As long as your potential satisfy these relations, you can get inflation. Now, essentially, all these models that are known as single fields low roll inflation model are characterized by a phase during which the scalar field undergoes a phase of slow roll evolution on the inflationary potential. The only thing you actually need to require is that your potential has a plateau which is flat enough to allow this phase of slow roll evolution. And this essentially implies satisfying these relations here. However, the point I want to stress again is that these relations do not fix the inflationary potential. So the question becomes, how can we say something more about the inflationary universe? How can we constrain the inflationary potential and the properties of the inflationary universe? Well, we can do so thanks to the predictions of inflation. So in this part of the lecture, I will try to understand what inflation actually predicts in terms of observational quantities. And in particular, the thing is that we can try to understand more about inflation thanks to the observations of the cosmic microwave background radiation. I told you before that we measure these photons, we measure CMB photons. All of them share the very same physical temperature, but we observe some temperature anisotropies, some fluctuations in the temperature of these CMB photons that are of order of 1 part in 10 to the power of 5. These temperature anisotropies and also polarization, as we shall see, are very, very important to understand inflation and inflationary universe, because we believe these temperature anisotropies to originate during inflation. And the reason is actually quite intuitive to understand. The evolution of the scalar field on the potential will not be classical. The scalar field will undergo some quantum fluctuations during its evolution in the potential. These quantum fluctuations will be stretched on super horizon scale during inflation. They will re-enter the causal horizon in the radiation-dominated universe, in the matter-dominated universe, and they will source irregularities in the energy density of the universe. And these irregularities in the energy density of the universe will imprint the cosmic microwave background radiation. So these temperature anisotropies that we do observe in the cosmic microwave background radiation that are observed with a very good precision by the Planck satellite are, we believe, originated during inflation. And so what I will try to do now is to characterize the predictions of inflation in terms of these quantum fluctuations and to link them to the observations, link them to the cosmic microwave background observations. I will follow the following strategy. I will start studying the quantum fluctuations of a free scalar field in a de Sitter spacetime. This is just an exercise. It's a very simple exercise, in fact, but it's very important because, as we shall see, we can borrow a large part of the results simply because during inflation we have a scalar field and the spacetime is nearly de Sitter. So once we are done with this exercise here, well, we can, most of the work is already there. Then we will try to understand what are the predictions of inflation in terms of primordial perturbations. We will derive the expression for primordial scalar modes, and we will derive the expression of the spectrum of primordial tensor modes, primordial gravitational waves. We will define both these perturbations, and we will try to understand why we expect inflation to produce them. Once we derive the expression, the predictions of inflation for primordial perturbations, I will try to connect them to what we actually observe in the cosmic microwave background radiation. So we'll give you an introduction to CMB temperature and polarization anisotropies. We will define the angular power spectra of temperature and polarization anisotropies. And we will try to understand how the primordial spectra predicted by inflation are related to the CMB angular power spectra that we measure in the cosmic microwave background. Once I'm done with that, we will try to understand what current observations tell us about inflation, and I will give you a state-of-the-art overview in terms of observational constraints. So let's start from the first point. Let's start studying the quantum fluctuations of a free scalar field in a de Sitter spacetime. To do so, I will start with a very simple action. I will start by the action of a free scalar field. This is just the action of a free scalar field. I'm not saying anything about the metric tensor right now. I'm not imposing that we are in de Sitter. This is just the action of a free scalar field. In general, if we are interested in studying fluctuations in the scalar field, the easiest thing you can possibly do is to split the scalar field into a background value, which will just depend on the cosmic time, plus some fluctuations delta phi. And the fluctuations delta phi will depend on the cosmic time and the spatial coordinates. These fluctuations delta phi in the Fourier space will obey the Mukhanov-Sasaki equation, which is this equation here, where U is a field redefinition given by the Fourier modes of the field delta phi for each wave number k times the scale factor a. How can we get the Mukhanov-Sasaki equation? You can start from the Klein-Gordon equation that we derived before. If you're interested in the equation of motion of the fluctuations delta phi, you can write down the Klein-Gordon equation for the fluctuation. You can switch to conformal time, which is just a redefinition of time, which is useful in order to have the metric tensor to be conformally equivalent to Minkowski. This is nothing but the Klein-Gordon equation in conformal coordinates. And then you can expand in Fourier space this field delta phi. This is nothing but a Fourier expansion. You have some Fourier modes delta phi for each wave number k, and you have some coefficients of the expansion b for each wave number k. And then you have the complex conjugate here. Once you expand this delta phi, this field in Fourier modes, you can plug delta phi in the Klein-Gordon equation. You can derive the Klein-Gordon equation for the Fourier modes delta phi for each wave number k. And then you can perform the field redefinition, and you can get the Mukhanov-Sasaki equation. So the step-by-step derivation of the Mukhanov-Sasaki equation is this one. I want to study two different and very important limits of the Mukhanov-Sasaki equation. The first limit is the so-called ultraviolet limit, where the wave number k is much larger than a double prime over a. Even this ultraviolet limit, which is called ultraviolet because you are looking at very small scales, so at ultraviolet frequencies, the Mukhanov-Sasaki equation simplifies because you can just get rid of a double prime over a in the square brackets because that's negligible compared to k squared. And you can write down this equation, this simplified version of the Mukhanov-Sasaki equation in the ultraviolet limit as a solution, which is given by this equation here. And you see that you have two integration constants. You have a and b that you can fixing the initial condition, and we will do that later. But you see that this solution is telling you simply that the Fourier modes will undergo some oscillations in the ultraviolet limit. So this solution is just showing some oscillations. On the other hand, you can consider the infrared limit, where k is much smaller than a double prime over a. In this case, you can get rid of k squared in the square bracket. And this solution, this equation has a very easy solution, which is the wave mods u of the field k, sorry, the field u for the wave number k should scale proportionally to the scale factor, because you see that this equation will simply become a double prime minus a double prime equal to 0, and it is satisfied. But if you remember the definition of U, well, U was defined as delta phi times A. So if U has to evolve proportionally to the scale factor, this means that the wave, the Fourier modes delta phi for each wave number k should approach a constant value in the infrared limit, if you want, on super horizon scale. This phenomenon is known as mode freezing, and it is very important because it's telling us that this delta phi will approach a constant value in the infrared limit. That is a very important and general result. Good. You see here in this figure, this is just the numerical solution of the Mukhanov-Sasaki equation, and you can find this behavior. You see that when you move towards the so-called infrared limit, this solution approach a constant value. However, so far, I didn't say anything about a double prime over a. This is just there, and I consider two different limits of this equation. What I want to do now is to use the information that we are interested in at de Sitter spacetime. If we are interested in a de Sitter spacetime, we actually know who a double prime over a is. And a double prime over a is given by 2 divided by eta squared, where eta is the conformal time. So when you impose that you are in a de Sitter geometry, in a de Sitter universe, this is your Mukhanov-Sasaki equation in a de Sitter universe. And this equation here has a solution, a general solution, which is given by this expression here. Again, you have two integration constant, a and b, that you need to fix by fixing the initial conditions. Now, what initial conditions we should use is quite debated. The standard choice in the literature is to fix the so-called Bunch-Davies initial conditions that, as we shall see in the next slide, will correspond to fix a vacuum state when we will switch to the quantum regime. The Bunch-Davies initial conditions means fixing A equal to 1 and B equal to 0. And hereafter, I will just fix the Bunch-Davies initial conditions. Once we fix these initial conditions, we have everything we need. We have the expression of delta phi in Fourier space. This will depend on this Fourier mods U. If we solve the Mukhanov-Sasaki equation and we fix the initial condition, we know what is U for each wave number k is given by this expression here. So we have everything we need. And so we are ready to switch to the quantum regime. So far, this was a classical treatment of these fluctuations. I didn't say anything quantum, it was just classical field theory. Now I want to quantize, and to quantize these objects, I will follow the so-called canonical quantization, which means we will promote delta phi, these fluctuations, to be operators. And this means promoting the coefficients of the Fourier expansion to be operators. And so B for each wave number k will be an operator, and I will denote it with this hat. And B star, where star was the complex conjugate, will become B dag, where this is no longer the complex conjugate, it will be the Hermitian conjugate. And when these objects are promoted to be operators, we can assume the commutators, this relation for the commutators. In particular, we impose that the commutator between B for the wave number k and B dag for the wave number k prime is a Dirac delta function, k minus k prime, and we will impose that all the other commutators are equal to 0. This is nothing but the canonical quantization that probably you are already familiar with. Once we assume these commutators, well, now these objects have a clear physical interpretations. And in particular, the operator B dag and B will be interpreted as creation and annihilation operators, respectively. And this defines a vacuum state for your theory. The vacuum state is defined as the state where the operator B acting on the vacuum state will give you 0, while the operator B dag acting on the vacuum state will give you some excited state. In fact, you can build a Hilbert space for our quantum field theory by defining a set of states representing the number of particles and their momenta that are defined in terms of the creation and annihilation operators as follows, as given by these equations here. This is just a technical detail for those of you that are interested in the Hilbert space of our quantum field theory. But the thing I want to say here is that before I told you, when we fix the initial condition, we implicitly fix the vacuum state of the theory. And this is the reason why, because now the vacuum state of our theory is defined in this way. And if we change the initial conditions, if we change A equal to 1 and B equal to 0, which corresponds to the Bunch-Davies initial conditions, we will change the vacuum state of our theory. You will get some different vacuum state when you will perform the canonical quantization. So what is the interpretation of these Bunch-Davies initial conditions? Well, essentially, you are requiring that in the ultraviolet limit, your space-time is Minkowski, and that the vacuum state of your theory is defined as the state where there are no particles. However, different initial conditions have been proposed, and if you are interested in these aspects, you can refer to the literature for non-standard choices of the initial conditions. Nice. So finally, we have an object, a quantum object, which represents the quantum fluctuation of a scalar field in a de Sitter universe. What I want to do now is to compute the easiest statistical correlator that we can possibly have, namely the two-point correlation function around the vacuum state. I want to compute this matrix element here. Simply the two-point correlation function, and in particular, I want to compute the primordial spectrum of the quantum fluctuations of a scalar field in a de Sitter spacetime P, which is just defined by this relation here. You can do the calculation. The step-by-step calculation is given here to get the expression of the spectrum of these quantum fluctuations. Essentially, you start from the expression we got for the quantum fluctuation of the scalar field. When you plug this expression in the two-point correlation function here, you have just one non-vanishing matrix element, which is represented by vacuum state B for the wave number k, B dag for the wave number k prime vacuum state. You can easily compute this matrix element with the following trick. You just add this operator here, which acting on the vacuum state is 0, so you are not doing anything, but this becomes the commutator between Bk and B dag k prime, which is nothing but a delta function. So the delta function will select just one k in this integral here, and you can simply solve the integral, identifying the primordial spectrum for the quantum fluctuations of the scalar field. Again, the calculation is done here, and it's also done in the notes if you're interested in doing it yourself. It's not difficult to repeat. And once you do so, you get this expression for the spectrum of the quantum fluctuations of the scalar field. And you see that in the so-called super horizon limits, where k is much smaller than a times h, this spectrum approaches the value of h squared divided by 2k cubed. Since we do not want in cosmology explicit dependencies on the wave number k, we can redefine the so-called dimensionless version of the spectrum, which is defined as k cubed divided by 2 pi squared the spectrum. And you see that this redefinition, this dimensionless spectrum on super horizon scales approaches the value, or a constant value, because the Hubble parameter is constant in a de Sitter geometry. And this constant value is h divided by 2 pi everything squared, where k is much smaller than a times h. So these exercises were interesting because we learned that the primordial spectrum of the quantum fluctuations of a scalar field in a de Sitter universe is constant on super horizon scale. Of course, this was an exercise because we were just interested in a de Sitter universe and the quantum fluctuations of a scalar field, but it is an important exercise. And perhaps you can already see why, because during inflation, we have a scalar field and the space-time is almost de Sitter. So you can already anticipate that we can borrow a big part of the results we derived so far and apply them to inflation. However, when we deal with primordial perturbations predicted by inflation, there are a number of caveats and technicalities that we need to clarify and that we need to pay attention to. And in particular, the first thing that we can ask ourselves is what kind of primordial perturbations are produced during inflation. So now I will try to characterize the primordial perturbations produced by inflation. In general, in cosmology, we can classify 3 different types of perturbations by studying the way they behave under rotation. Or if you prefer, we can classify perturbations based on their helicity or spin. We have scalar perturbations that are invariant under rotations, or if you want, they have spin or helicity 0. We have vector perturbations that are those with helicity plus minus 1. And we have tensor perturbations that are those with helicity plus minus 2. We expect that during inflation, scalar and tensor perturbations will be produced. Why is that? Again, this is simplifying a lot the story, but essentially during inflation, you have a scalar field, an object which is invariant under rotation. Therefore, you do expect some amounts of perturbations that are scalar perturbations, invariant under rotations. On the other hand, during inflation, any degrees of freedom will be quantum mechanically excited. And what other object do we have, at least in the simplest models of inflation? We have a metric tensor. So we do expect some quantum mechanically excited fluctuations in the metric tensor that will give rise to some stochastic background of gravitational waves, a relic background of gravitons with spin plus minus 2. Therefore, some tensor perturbations. If you consider more advanced model of inflation, where you also have some vector degrees of freedom, then probably you can even have vector perturbations. However, vector perturbations will scale as 1 over the scale factor, so they will be redshifted away with the expansion of the universe, and typically they are not important. However, in this simple theoretical setup that I described so far, single field inflation typically expects scalar and tensor perturbations. And this is the first important thing to keep in mind. The second thing to keep in mind is that when we deal with perturbations produced during inflation, we need to pay attention to the fact that general relativity is invariant under diffeomorphism. And this brings the well-known problem of gauge invariance and gauge dependence, if you want. What is the thing? The thing is, these scalar perturbations produced during inflation will be stretched on super horizon scale during inflation. They will re-enter the causal horizon in the radiation and matter-dominated epoch, and they will source irregularities in the energy density of the universe. But when we deal with irregularities in the energy density of the universe, we need to pay attention to the coordinate system. Suppose that you live in a universe that is perfectly homogeneous and isotropic. Then requiring that you do not observe inhomogeneities in the energy density fixes the reference frame. There are some privileged coordinates, the so-called comoving coordinates. And if we are comoving observers in a perfectly homogeneous universe, we do not see any irregularities in the energy density of the universe. However, in a perturbed universe, the story is different because the splitting into an homogeneous part and some perturbation is no longer unique because it depends on the coordinate system. And we do not have any privileged coordinate system anymore because we have some intrinsic perturbations. And so perturbations themselves becomes gauge-dependent quantities. They depend on the coordinate system that we fix. So first of all, we need to fix a coordinate system. And secondly, if we want to characterize the predictions of inflation without caring about this issue, without caring about what coordinate system we choose, it is better to work in terms of gauge-independent quantities, namely quantities whose value do not change if we change the coordinate frame, if we change the coordinate system. On the other hand, when we will study primordial gravitational waves, well, primordial gravitational waves are gauge invariant at linear order. So they are essentially, life is a little bit easier when we deal with primordial gravitational waves because we don't need to pay attention to this problem. So let's start with the difficult one. Let's start with scalar modes. So when we want to quantify primordial scalar modes produced during inflation, if we don't want issues with the gauge problem, we need to use some gauge-independent quantity. And one gauge-independent quantity that is usually employed to characterize primordial scalar modes is the so-called primordial curvature perturbation zeta, which is defined in this way, where capital psi is telling us about the curvature of hypersurfaces at constant conformal time. This quantity here, by definition, is gauge-independent. If we change coordinate system, its value does not change. So we can fix whatever coordinate system we like. And this is the smartest thing that you can possibly do is to probably choose the so-called zero spatial curvature gauge, where capital psi is equal to 0. If you do so, you can simply relate zeta to the fluctuations of the inflaton field. The only thing is that you have this prefactor here, which is given by h divided by phi dot. Other than that, zeta becomes proportional to the quantum fluctuations of the inflaton field. So now we want to compute some correlators. We can compute the two-point correlation function of zeta. If zeta is gauge independent, the two-point correlation function of zeta will fully characterize the spectrum of scalar modes produced during inflation. And now this is very easy to do because the only thing you need to take into account is this prefactor here. Other than that, you can simply repeat the very same exercise we have done for this quantum fluctuations of a scalar field in a de Sitter universe. Therefore, you can exactly borrow the results we derived so far before for the de Sitter universe. The only thing you need to take into account is this prefactor here. Therefore, you can easily derive the spectrum, the expression for the spectrum of primordial scalar modes predicted by inflation. The step-by-step derivation is given here. Essentially, you can just repeat the very same calculation we did before, accounting for this prefactor. In this last line, I'm also using these Lorentz conditions to write the primordial scalar spectrum in terms of these Lorentz parameters, epsilon. Good. So we derived the expression of primordial scalar modes. Now let's try to understand how we can derive the expression of primordial gravitational waves. So primordial gravitational waves, or tensor modes, are described in terms of the transverse and traceless part of a symmetric 3×3 matrix Hij, which is given by this relation here. So the equation of motion of Hij can be derived linearizing the Einstein equation. You can write down the linearized Einstein equation. Delta G mu nu is equal to delta T mu nu. Delta Ij is given by this expression, while delta Tij is equal to 0 if you assume that T mu nu is the stress energy tensor of a perfect fluid with no anisotropic stress. From the linearized Einstein equation, this means that the term in round bracket should be equal to 0. And this defines the equation of motion of Hij. Then you can essentially expand these objects in the Fourier space. And for each wave number k and each polarization state, we have two different polarization state, plus and cross, because these things have two internal degrees of freedom because they have spin 2. And for each polarization state, you have this equation of motion here for the Fourier modes. You can just redefine the very field redefinition we performed for the Mukhanov-Sasaki equation when we derived the Mukhanov-Sasaki equation. And you find out that in Fourier space, the wave modes H satisfy the Mukhanov-Sasaki equation. Therefore, you can repeat the very same calculation we have done so far. We have to derive the expression, the power spectrum of primordial gravitational waves. The only thing you need to take into account is that you have two different polarization states. So there is a factor of 2. And you also need to make sure that your field U is canonically normalized. So there is a prefactor that makes the field to have the correct units. Once you account for these prefactors, you see that you can borrow the result we derived before, and you see that we can easily derive the expression for the primordial power spectrum of gravitational waves predicted by inflation. Again, unfortunately, I didn't have time to do the calculation explicitly, but you can find it in the notes, and there is the step-by-step derivation in the slide. It's not difficult, I hope, to follow. Nice. So we have the expression for the primordial spectrum of scalar modes predicted by inflation, the expression for the spectrum of primordial gravitational waves predicted by inflation. Both of them are essentially given on slow horizon scale by the Hubble parameter and some slower parameters. These quantities, if the universe is de Sitter, are constant. If the universe is almost de Sitter, as you need to require for inflation to end, are nearly constant. They evolve very slowly with time. That's the reason why you expect the primordial spectra to have a very weak scale dependence. They are not exactly scale dependent, but they are almost scale independent. For this reason, you can essentially adopt a power law parameterization that is widely used in cosmology. So for both the spectrum of scalar modes and the spectrum of tensor modes, you can adopt a power law parameterization where you have an amplitude. In the scalar case, you have the scalar amplitude AS, and you have some spectral index NS here. For primordial gravitational waves, you have a tensor amplitude, which is usually parameterized in terms of the so-called tensor to scalar ratio R, and you have a tensor tilt. You can express these spectral parameters in terms of the Slurol parameters, which I remind you contains information about the inflationary potential and its derivatives. But for the moment, what is important is that inflation predicts primordial spectra that can be well approximated by power laws on this, above all on the scales corresponding, on the frequencies corresponding to the cosmic microwave background radiation. And this is important because the next step will be to link these theoretical predictions to what we observe in the cosmic microwave background. So now we will enter the third part of this strategy. We have seen what inflation predicts. We have seen that inflation predicts this power law primordial power spectra. Now we need to try to understand how these primordial spectra relate to what we actually observe in the cosmic microwave background radiation. So the question is, how can we characterize what we observe in the cosmic microwave background radiation? I told you before that the very first thing you can possibly do is to measure the temperature of CMB photons. All these CMB photons share the very same temperature within some fluctuations. Therefore, we can split the field that defines the temperature of CMB photon, T, which will depend on the conformal time, the coordinates, and the direction in the sky we observe, P. Well, we can split this field in a homogeneous background part, the temperature that all these CMB photons share at first approximation, plus some fluctuations delta T over T. I will redefine the fluctuations delta T over T as capital theta, which is known as brightness function. This is a very common notation used in the literature that I will follow. You see that the brightness function that just defines the temperature and isotropism we observe in the cosmic microwave background will depend on the conformal time, the coordinates, and the direction. Now, this brightness function is strictly related with what we observe in the cosmic microwave background, because we observe differences in the temperature of the CMB photons in different directions in the sky. We have a clear spherical symmetry in this problem, right? Because we can measure photons arriving from any direction in the sky. So we have a spherical symmetry in the problem that we can use to expand this brightness function in spherical harmonics, YLM. And there will be some coefficients of this expansion, ALM. The coefficients will depend on conformal time and coordinates. The spherical harmonic will depend only on the direction we observe. So we can split the dependence between coordinates, time and spatial coordinates, and the direction, thanks to the spherical symmetry that we have in the problem. Why is that important? Well, this is important because spherical harmonics are very nice functions. They are orthonormalized, meaning that their integral over the solid angle of the spherical harmonic YLM times the spherical harmonic YL prime M prime star, where star is the complex conjugate, is given by delta LL prime delta M prime. They are orthonormalized. And we can use these properties essentially to reverse this equation. The step-by-step derivation is done here, but essentially you can reverse this equation and you can express the coefficients of this function. You can express ALM as an integral over the solid angle of the brightness function theta times some spherical harmonic. Why is that important? This is important because we can measure the brightness function, right? We can measure the temperature and isotropism in the cosmic microwave background. We can measure these differences in the temperature of CMB photons. Therefore, this is telling us that we can actually measure these coefficients of this function. We can measure ALM because of this relation. What's the caveat? The caveat is that we can measure these coefficients only here, meaning on this planet. We can run some CMB experiment, and now at this precise cosmic time. Other than that, we can measure these coefficients of this function. However, there is yet another element there is yet another difficulty, because we can measure these coefficients of this function, but we cannot make any theoretical predictions for these coefficients because they are just coefficients of spherical harmonics expansion. So we can measure them, but then we don't have any theoretical prediction to test our observation. So what do? Well, the thing is that we cannot predict anything for this value of the specific coefficients, but we can make predictions about their statistical properties. And in particular, we believe that these coefficients originate during inflation because of the quantum fluctuations of the impedance fields. And if the fluctuations produced during inflation were Gaussian, then we expect these coefficients to be Gaussian as well. And this is very important because if these coefficients are Gaussian, the two-point correlation function of these coefficients is everything you need. They just contain full information because the higher order correlators are simply related to the two-point correlation function if they are Gaussian. Another thing is that we believe the universe is invariant under rotation. We believe that at large scales, the universe is isotropic. And this is even more true when the universe was younger than now. And if we assume invariance under rotation, well, invariant under rotation implies that the average of these coefficients over an ensemble of universes that share the same properties that our universe should be zero. Suppose that you have 100,000 universes that share the very same properties as our universe. The average of these coefficients on this ensemble of universes should average out. On the other hand, as I told you before, we expect the two-point correlation function, we expect the variance of these coefficients on this ensemble of universes to be non-zero. So we expect some non-zero variance that is here quantified by these coefficients that they call CLTT, which represents the angular power spectrum of these temperature anisotropies. So you see, we can make predictions about the statistical properties because now you can give me a model of your universe. I can compute these coefficients CLTT predicted by your model of the universe. And now you will say, then we can test our observations against this prediction. But there is yet a final difficulty here, which is that we don't have an ensemble of universes that share the same properties as our universe. We have just one universe. So how do we actually test our observations? Sorry, I lost this. Okay. To do so, you can simply estimate CLTT, this angular power spectrum from observations by averaging over M. I told you we can measure the coefficients ALM. We can simply take the average over the momentum M, and you can estimate from observations the angular power spectrum of temperature anisotropies. So finally, you have some theoretical predictions for CLTT, and you can estimate CLTT from observations simply taking the average. You can measure them, you have some theoretical predictions, you can test your data against the theoretical predictions. And this is what has been done by the Planck collaboration. We can measure CLTT, we can measure the angular power spectrum of temperature anisotropies. If we assume a lambda CDM cosmology, we have some predictions for the spectrum of temperature anisotropies, and there is a remarkable agreement between the theoretical predictions and what we actually observe. The only thing I want to say is that if these coefficients ALM are Gaussianly distributed, if they are Gaussian, and we expect they are at least a very high precision because of the physics of inflation, then this CL is distributed as a chi-square with 2L plus 1 degrees of freedom. So there is an intrinsic statistical error that you need to take into account, which is known as cosmic variance, which is given by this expression here. And you see that it becomes important at low multiples, meaning at large angular scales. Having that said, you see that we finally have some theoretical predictions and some observations. You can do something very similar for CMB polarization. I don't have time to explain CMB polarization, but there are some written notes on polarization. And essentially what you can do for polarization is to expand not in spherical harmonics, but in spin-weighted spherical harmonics. You need to take into account that you have two different polarization states in the cosmic microwave background. You have E-mode polarization, which is parity even. You have B-mode polarization, which is parity odd. Other than that, you can use a very same formalism to define the angular power spectrum of E-mode polarization B-mode polarization and the cross-spectrum between temporal and E-mode polarization. So to recap, we observed the cosmic microwave background. We have some temporal anisotropies. From the temporal anisotropies, we can derive predictions and observations for the angular power spectrum of temporal anisotropies, CLTT. For polarization, we can distinguish E-mode polarization and B-mode polarization, and we can derive the spectrum of E-mode polarization, CLEE, and the spectrum of B-mode polarization, CLBB. If we assume that parity is a conserved quantity in our universe, there is only one additional non-vanishing angular power spectrum, which is the cross spectrum between temperature and E-mode polarization, CLTE. So essentially, you can extract 4 independent angular power spectra from the observations of the cosmic microwave background radiation. Great. We have here the different angular power spectra we observe in the cosmic microwave background. We have here the primordial power spectra predicted by inflation. What is the relation between them? The easiest way to relate these angular power spectra to the primordial power spectra predicted by inflation is by means of the so-called transfer function. So essentially, for all these CL, for CLTT, CLTE, CLEE, CLBB, you can distinguish between a contribution coming from primordial scalar modes produced during inflation and a contribution coming from primordial tensor modes produced during inflation. I will call them CL scalar and CL tensor. CL scalar is given by an integral over the wave number k of the primordial scalar spectrum predicted by inflation times some scalar transfer functions. The tensor contribution is going to be given by an integral over the wave number k of the primordial tensor spectrum predicted by inflation times some tensor transfer function. The scalar and tensor transfer functions encode information about the full Einstein-Boltzmann system of coupled equations that you need to solve for cosmological perturbation theory. There is no simple analytical expression for that. You will need to derive the full set of Einstein-Boltzmann equations that will take 60 hours, which I don't have. But you, as we shall see possibly in the second part of the lecture, you can compute these objects numerically using some Einstein-Boltzmann solver codes such as CAMP class and so on and so forth. Great. So to recap, any CL can be divided by a contribution coming from scalar modes and a contribution coming from tensor modes. We can do the following exercise. For each of these 4 spectra, for CLTT, for CLTE, for CLEE, and for CLBB, we can compare the contribution coming from scalar modes with the contribution coming from tensor modes. If we do this exercise, you see that the contribution coming from scalar modes is always dominant compared to the contribution coming from tensor modes, both in CLTT, CLTE, and CLEE. However, we are lucky enough because the contribution in CLBB in the angular power spectrum of B-mode polarization is dominant compared to the dancing counterpart at small multiples. So the best thing you can do to constrain primordial tensor modes produced during inflation is to look at B-mode's polarization at large angular scales. CLBB in the multiple range, I will say between 2 and 100. Nice. So now, with this picture in mind, I will try to give you an idea of what are the observational constraints that we can obtain from the most updated cosmological data, and in particular from CMB data. I told you before that the most precise CMB experiment that we have in cosmology right now is the Planck satellite. Planck is measuring with very good precision the spectrum of temperature anisotropies, CLTT, the spectrum of E-mode polarization, CLE, and this cross-spectrum between temperature and E-mode polarization, CLTE. CLTT is well measured between 2 and 2,500 in multiples. CLE is also measured between 2 and 2,000 in multiples. For CLTE, we typically only consider data between 30 and 2,000 in multiples. So we can use, of course, these data from the Planck satellite, but I told you in these three spectra, the dominant contribution is that coming from scalar modes. So if we want to achieve a good constraining power of primordial gravitational waves on tensor modes, we also need to account for beam mode polarization. And Planck is not doing well with beam mode polarization. Therefore, we can try to use some other CMB experiment. And the experiment, which is currently most constraining on beam mode polarization at scales of interest for inflation, is BICEP kick array experiment, which is working at the South Pole, and that is measuring beam mode polarization very precisely at the scales of interest for primordial gravitational waves for inflation. So we achieve the best constraining power when we combine Planck and BICEP data together. So let's try to understand what observational constraints we can get if we combine Planck and BICEP data together. And let's start from the constraints on the primordial spectrum. In particular, when we combine Planck and BICEP, we can try to constrain the amplitude and the spectral indices of this primordial spectra. And in particular, you see that we measure the spectral index NS to be different from 1 at more than 8.5 standard deviations. And this is considered one of the most important indirect evidence supporting inflation, because in all these simple models of inflation, typically you expect the spectral index to be different from 1 because of the evolution of the scalar. On the other hand, we do not measure the amplitude of primordial gravitational waves. We do not measure the tensor to scalar ratio, but we have a very tight constraint on the tensor to scalar ratio, which is constrained to be smaller than 0.035 and 95% confidence level. These observational constraints are very important because now what you can do is to use these relations, these Lorentz relations that relate these spectral parameters to these Lorentz parameters to derive constraints on these Lorentz parameters. And in particular, we can derive constraints on epsilon and eta, these Lorentz parameters epsilon and eta, that are defined in terms of the inflationary potential and its derivatives. We measure eta to be negative and different from 0 at very high statistical significance. We do not measure epsilon, we have just an upper limit. It is constrained to be smaller than 0.0022 and 95% confidence level. And so you see that these observations set a very strong hierarchy between these two parameters, because in absolute value, eta is measured to be much larger than epsilon. And this is very important because now these constraints limit a lot your freedom to choose inflationary potential and inflationary models. You can give me a potential, I can compute the predictions of your potential for epsilon and eta. As long as your model falls within these probability contours, it is allowed by data. If your model falls outside these probability contours, it is ruled out by observations. Along the years, several models have been tested against Planck and BICEP data. A few of them are currently allowed by observations, and I would say that currently the benchmark theoretical scenarios for inflation is represented by Starobinski inflation, where inflation is controlled by a square Ricci scalar in the effective gravitational action. So it's an FOR theory of gravity, if you want. This model gives some predictions for the spectral index and the tensor amplitudes. Both of them are related to this number of equals before the end of inflation. If we follow the Planck paper, this number is constrained to be between 50 and 70, but if we account for the physics of reheating, we can narrow down this range between 55, 65. Anyway, we can test these theoretical predictions against Planck and BICEP data, and Starobinski inflation emerges as one of the best fitting model, or maybe the best fitting model given current observations. And this is the reason why essentially all future CMB experiments are actually designed to reach a sensitivity on the tensor amplitude that is enough, that will be enough to either confirm or rule out Starobisky or Starobisky-like models of inflation. And this is more or less the current state of the art in terms of observational constraints on the inflationary universe. I would say I can stop here the theory part of the lectures.
So do we have any questions? Sayantan?
Yeah, sorry, can I ask just quick questions actually? Yeah, so very nice talk. So I was just wondering that when you wrote the Sasaki-Mukhanov variable, I mean the gauge invariant one, you probably took out that there is a Laplacian part, right? I mean, even when we take in the Bardeen gauge invariant quantity, we take the Laplacian. Is it because of the super Hubble horizon limit? I mean, like the k is much less than 1 because of the lambda is large, or I mean, is that the reason, or is it like the general reason? Like, I mean, so there should be a Laplacian part in the U double prime and the others, right?
Yeah, but yes, but the questions were derived in super horizon limit. That's the expression of the primordial spectrum in the super horizon limit. So the Laplacian becomes negligible in that limit.
Okay, so I'm asking that if I want to extend this tensor perturbation for the quintessence law, which is the late time acceleration, then I have to keep on the Laplacian to keep track of this.
Sure.
I mean, I understand for inflationary it is fine, but if I want to do it for quintessence, then I have to keep on the Laplacian, right?
Yes, you need. I think so.
Okay. Yeah. Thank you very much.
So this is the shared Google Drive folder where you can find the material for the theory part. And there is this folder here, which is called Hands-on Session. And inside the folder, you can find some examples, some Jupyter notebook that you can actually use. There is a notebook which is an introduction to CAMB, which is the one that I'm going to explain today. But there is also a notebook which gives you an introduction to GEDIS, where GEDIS is a software you can use to analyze the MCMC chains. There is a notebook which is a theoretical introduction to the MCMC procedure that you can actually use in cosmology. There are some notes about the MCMC analysis, how you can perform this MCMC analysis and all these things. And then finally, there is a notebook which gives you an introduction to the most important local universe probes, so BAO and supernovae. So there is quite a lot of material and that you can play with. Also, there is a folder called data. Inside this folder, there are the BAO dataset, the Pantheon Plus data, and the Planck data for the spectrum of temperature and isotropies. And there are some MCMC chains that I produce for different models of cosmology, just if you are interested in playing with these chains. And they are here and feel free to use as you like. So now I would like just to briefly discuss this notebook here, which is Introduction to CAMB, where CAMB is code for anisotropies in the cosmic microwave background. Is one of the Boltzmann solver codes that is most used in cosmology together with class. There is no real reason to use CAMB or class. They are just two very great codes that you can use. There are some implementation details that are slightly different between the two codes. But overall, if you're interested in quite standard models of cosmology, they give the same predictions and the same result. So today I will just show you how you can use CAMB. And in particular, in this notebook, there are different steps that you can follow to do different things. It's a little bit oriented towards inflationary cosmology because I want to show you how we can solve numerically the Einstein-Boltzmann equations to get the transfer functions and things like that. But the very first thing is that you can install CAMB on your laptop. So here my expertise is limited to installing CAMB on Mac because I never used any other software. So I don't know, but if you are using a Mac, it's quite easy. you can just download Xcode, Gfortran, and on this link, and then installing CAMB is pretty much easy. If you are using some different laptop, I think you can find something similar to this notebook online, and they can explain you how you can install CAMB on different laptops. It shouldn't be difficult though. Once you install CAMB, the second step is to import CAMB. You just need to give the path to the folder where CAMB is installed in your laptop, and then you simply import CAMB as a Python module. Indeed, the very nice thing of CAMB is that there is a Python wrapper, and you can use it as a Python module. The thing in CAMB, you can do many things, of course. The very first thing you can do is so this code is taught to compute the CMB angular power spectra that we discussed during the theory part. This CMB angular power spectra depend on the cosmological parameters and their values. So the very first thing is to fix the values of the cosmological parameter. I'm doing here in this part of the code. There are the standard 6 parameters of the Lambda-CDM cosmology that are the Hubble constant, the baryon energy density, the cold dark matter energy density, the spectral index of primordial inflationary perturbations, NS, that we discussed, the amplitude of primordial perturbations, AS, that we also discussed, and the optical depth at reionization tau. Then there are a lot of other key parameters for cosmology, such as the dark energy equation of state. It's the parameter that can possibly describe its evolution over time. And then there are other parameters related to inflation, such as the running of the spectral index, the running of the spectral index, the curvature density parameter, omega k, the total mass of neutrinos, the effective number of relativistic degrees of freedom, the lensing amplitude, and so on and so forth. These are all parameters that in Lambda-CDM are fixed to the values that I am giving here. So the equation of state for dark energy is -1 because we believe it's a cosmological constant. Omega is, WA is equal to 0 because we believe there is no time evolution. We assume that NS is constant, so the running and the running of running is 0. We assume that the universe is flat, so omega k is equal to 0. We can use the value of 0.06 electron volt for the total mass of neutrinos. We believe there are 3.044 relativistic degrees of freedom at recombination that are the 3 families of neutrinos plus an additional corrections that is coming from the non-instantaneous neutrino decoupling. And then we assume that the lensing amplitude is 1 as predicted by the Lambda-CDM model of cosmology. And then there are many other parameters that are related to the precision you can get in the code, if whether you want or not primordial tensor modes, and so on and so forth. There are many, many parameters that you can fix to different values, and they are well explained in this params.ini that you can find in the folder any files when you start COMP. However, in this part of the code, I'm just fixing the values of cosmological parameters to the Lambda-CDM cosmology. And in the notebook, the idea is to show you how powerful these numerical codes are right now. So we can do a lot of things. Once we fix the cosmological parameter, we can compute the full cosmology. And in particular, we can use this command here to get the results giving our cosmological parameters. And this will return you a dictionary which contains full information about the universe, giving some cosmological parameters. And there are a large number of different parameters related to different evolutionary epoch of the universe. So depending on your field of expertise and research interest, you can play with these outputs and these results. You can even compute parameters related to the transfer functions. You can compute the right parameters, such as the age of the universe, the angular size of the sound horizon. So you have access to full information about your model of cosmology given some values of the cosmological parameters. The thing is that you can also compute the CL. You can compute the different angular power spectra for temperature and polarization anisotropies. You can do it very easily with this command here. And this will return this DL, where the DL is just CL times this prefactor here, which depends on the multiples L. Anyway, this will return you the DL for the different spectra, both length and unlength. And you can plot them. There is the script to plot the CL, so you can just follow this script. This is just for plotting them. So this is the CL, TT, the spectrum of temperature and isotropies. This DL, EE, the spectrum of E-modes polarization. This is DL, TE, the cross spectrum between temperature and E-modes polarization. And this is DL, BB, which is the spectrum of B-modes polarization. And for instance, you see that the unlength DLBB is equal to 0, which is also a prediction of lambda CDM. Nice. Then you can, so these are the CMB angular power spectra that are very important, but you can also compute the primordial spectra predicted by inflation. In fact, you use the power law parameterization and giving your initial values of cosmological parameters for AS and NS, you can in fact extract the value of the primordial spectrum for scalar modes predicted by inflation, and you can plot it. There is the code to do so here. And if you remember the theory part of the lectures, I told you, well, the easiest thing you can possibly do to relate the primordial spectra predicted by inflation to the CL is to use the transfer matrix, the transfer functions. The transfer functions depend on a set of Einstein-Boltzmann equations that you need to solve numerically. Well, you can use this code to get the transfer functions, and this is how you can do that. The output is explained here, so you can just refer to this notebook. You can compute the transfer functions for scalar modes, you can compute the transfer functions for tension modes, and you can plot them fixing either the wave number k or the multiple. Here I'm fixing the multiple 2, and I'm plotting the transfer function for temperature and isotropies at multiple 2 as a function of the wave number k, and this is the result. I can do the same fixing the multiple L equal to 5 and instead of temperature and isotropies, I can focus on E-modes polarization. And again, the way you can do so is explained in the notebook, and this is the transfer function itself. And so you can really play with CAMP to get all the quantities you are interested in. Another thing that you can do, always oriented towards inflationary cosmology, is that suppose you have a non-standard model of inflation, and your standard model of inflation predicts a very weird primordial spectrum, such as the green one in this figure, when you can give to CAMP a very weird primordial spectrum for scalar modes, and it is able to compute the corresponding CL, giving this non-standard primordial spectrum. And the way you can do so is also detailed in the notebook. And essentially, you see that you can compute the CL, giving in input your primordial spectrum predicted by your model of inflation. So whatever favorite model you have, if it predicts some modulation, some weird behaviors in the primordial spectrum, you can code it in CAMP very easily, actually, and you can follow this notebook. And for instance, here I am showing you the differences between the CL in the temperature and isotropies as obtained assuming a power law spectrum, which is the general prediction of inflation, and then a standard spectrum in green in this figure. And you see that the differences are not very large across the different multiples. And so you can try to figure out what kind of observational implications your non-standard model of inflation can possibly have in the CL, coding them in CAMP very easily. So again, you can follow this notebook, and there are many other sources in the literature you can follow if you are interested to play with CAMP and getting the numerical results on different observations and observational quantities. Another notebook that probably is useful for those of you that want instead to perform MCMC analysis is this one. where I briefly provide you some examples of how you can use GetThis. GetThis is a code that you can use for analyzing the MCMC chains. I think some other lecturers at some point might give lectures on how you can do the MCMC sampler and all these things here, but I'm not covering that part. I'm instead covering how you can analyze these MCMC chains. When you do the MCMC analysis, when you do the Markov chains Monte Carlo analysis, you get typically some file that you can find in my shared folder in this path. These files are produced using Cobaya, which is an MCMC sampler. And essentially, you are interested in these kind of files, the one that contains information about the so-called MCMC run. So this is these files store all the information, all the relevant information that you can extract using GetThis. And in particular, in the notebook, I'm showing you how you can read these chains, how you can test whether they converged. So there is this R-1 quantity that is called the Gell-Mann-Rubin factor. If your chains are converged, the Gell-Mann-Rubin factor must be very close to 0. So for instance, in these chains that I am reading here that are assuming a baseline lambda CDM cosmology, the R-1 is 0.007, so the chains are well converged. And then I am giving here a lot of examples about how you can, for instance, get the numerical constraints, the one I showed in the slides. There are some examples about how you can plot the one-dimensional probability distribution functions. There are some examples about how you can plot the two-dimensional distribution functions. So if you want, how you can marginalize in your parameter space and you can get the correlations between the two different parameters. For instance, here I'm showing you the correlations between H0 and the spectral index in lambda CDM. And these are the probability contours. The dark one is 68% confidence level. The light one is 95% confidence level. And you can even get 99% confidence level if you just change this variable. And so in this case, you see I also added the contours at 99% confidence level. Suppose that for some reason you don't want constraints at 68, 95, and 99 that will correspond to 1, 2, and 3 sigma if your posterior is Gaussian, but you want constraints for some reason at 20%, 40%, 60%, and 80% confidence level. Well, you can do that using this part of the script. And here I'm plotting the constraints, the correlations between these two parameters at 20, 46, and 80% confidence level. This is just in the event some of you are interested in non-standard statistical analysis. Then you can plot the so-called contour plots or triangular plots, where you can plot together two-dimensional, one-dimensional probability distribution functions. Again, the script to make this plot is given here. Both at 68, 95% confidence level and at 20, 46, and 80% confidence level. You can make three-dimensional plots. Suppose that you want to study the three-dimensional correlation between H0, the spectral index, omega matter. You can make this kind of plot from which you can see that when H0 is larger and S is also larger, but omega matter gets smaller, if you refer to the color bar. And this is useful if you want to study correlations between three different parameters. Then you can compare the results you get in different models. For instance, here I'm assuming that the spectral index is not constant, but it has a running. You can do the MC analysis, adding one more parameters, which is the running of the spectral index, and you can compare the results. This is just to show you how you can plot contours resulting from two different models of cosmology, and how you can make this kind of comparison. And you can do the very same thing I've done for one model. So you can plot the results for lambda CDM and lambda CDM plus the running of the spectral index. in contour plots, in three-dimensional plots, and so on and so forth. And then there is a nice thing that is the reweighting sample. This is a bit tricky to explain in a sense, but suppose that you run a model of cosmology which is not standard. Suppose you run W cold dark matter cosmology, where you leave the dark energy equation of state to be a free parameter. If you just use the CMB data, you get something like that. You get that H naught is no longer constrained. And now you see that it is very correlated with W, it's the equation of state of dark energy. And you have these kind of situations where H naught can be as large as 100 and as small as 60. So when your parameters are so broad and broadly distributed in the parameter space, you can think to reweight the constraints, assuming some additional likelihood. And for instance, we know that the Schuss collaboration is measuring H naught 73 plus minus 1. And there is a very easy way to introduce this information once you have the chains, which is reweighting these chains. And the procedure to reweight the chains is detailed here. It's just 3 lines of code. And once you account for these 3 lines of code, you can essentially get from the red contours that were focused only on the Planck data, you can reweight them with the Schuss prior in H naught and get the blue contours that are much more constrained. So you don't have to rerun the analysis from scratch, but you can use this reweighting sample methodology to reweight your chains. And I put this here because maybe it can be interesting for those of you that use this kind of data and procedures. I'm also giving some examples about how you can define new parameters. Suppose that for some reason you want to define a new parameter of your cosmological model that can be defined in terms of fundamental parameters. You can do so using the chains you already have. And here I'm detailing the procedure. For instance, I'm defining, starting from the constraints of sigma 8 and omega matter, I want to define the S8, where S8 is defined in terms of the other 2. There is a simple way to redefine parameters that I detail in the notebook as well. And you see that you can get the constraints in your defined parameter S8. And you have access to the full constraints and correlations with other parameters and so on and so forth. Finally, I'm also showing you how you can get the light stats, which is a file containing all the informations on all the parameters. And so whatever quantities you are interested to constrain, you can find these. And so these were just some notebooks that I am using to give you an idea of how you can use these codes. It's just meant to help you with your analysis and with your daily work as researchers. And I hope you can find them useful somehow. And I think that's it for the second part. Let me just say that if you want to practice a little bit with my notebooks, I give you here some exercises. Eventually, you can try to solve them. And these exercises are divided in very easy exercises, somehow easy exercises, and slightly more difficult or advanced exercises, both for CAMB and for GADIST. And that's it.
Thank you very much, William. I'm sure this is very practical for a lot of the people here. Any questions or comments on this?
So one is that tensor perturbations, you stop measuring them at some point. Is it because they're unconstrained? I missed that part, I think. Like we also, like in practice, we always have NS as one of our pre-parameters, but not NT.
The thing is, so if you compare the contribution of tensor mods and scalar mods, the contribution of tensor mods is always subdominant compared to the one of scalar mods. But tensor mods can leave some important imprintings in the B-mods polarization at large angular scales. So we can test primordial gravitational waves. And I also included the results for primordial gravitational waves here. I included the results on the amplitude of primordial gravitational waves. This is nothing but the amplitude of the spectrum of tensor modes. Why I am not using NT? Because if you assume these single field models of inflation, NT is related to the tensor amplitude by this equation here. And you see that both these parameters are related. So in the tensor spectrum, in fact, you have only 1 degree of freedom, which is the amplitude. Once you know the amplitude, you also know the slope within these simple models.
Again, in standard practice, what do you do with R? Do you like fix it?
No, you can vary it.
No, you can vary it, but like normally, like the baseline.
In Lambda CDM is fixed to 0, yes.
It's fixed to 0.
Yeah.
And so when you are connecting the primordial fluctuations, the spectrum to the CMB one,
yeah,
there happens reheating in between these two, right? Like the primordial is before reheating, and then CMB is of course after reheating.
Yeah, yes, that's true, but you don't account for the physics of reheating. So
the transfer functions don't depend on reheating.
Yeah, because essentially what you want to achieve during reheating is to reestablish all the standard model particles, right? So you typically, when you, at the end of inflation, the universe is empty, right? Because any particle is just blow up away and the universe is empty, but you have a lot of energy stored in the field. And the field will oscillate around the minimum of the potential, and then it will decay in other standard model particles. So you need to make sure that you have a theory which comes with a reheating phase, which is able to reestablish particles. After that, you can just derive the Boltzmann equations in the radiation-dominated universe, and that's how Camp and class work. They don't account for the physics of reheating.
Just one small thing is that, so while you were showing Camp in the last part,
right?
Yeah, you were showing like you have different primordial spectra, and then you can compute the CMB one. So is it done in the literature to go backwards? I assume it has been done, like reconstructing the primordials.
There are a lot of works about reconstructing the primordial spectrum. One is from Alberto, yes. And but there are many other works in this direction. Essentially, you can try to reconstruct this function, but it depends on the transfer function. So an assumption in that case is that you assume a lambda CDM cosmology. Another thing that you can do, and that has been done, is to study what kind of primordial spectrum you will need to solve double tension. And there are papers on that, and they show that if you have some very peculiar modulations in the primordial power spectrum, you can change the CL in such a way that you infer a value of H0 which is closer to shoes. So a lot of things have been done.
Thank you again, William. This has been really good to everyone as well. I think I speak for everyone. This was very informative. So, to the audience, please join us next week for the next training session. Thanks again, William.
Thank you.